From an executive dashboard, a system modernization project often looks like a well-oiled machine. Timelines are set, budgets are allocated, and migration phases are mapped. But the reality on the ground for the engineers actually doing the work is often chaotic, stalled, and deeply frustrating. Enterprise modernization programs rarely end in dramatic explosions. Instead, they die quietly. Budgets are gradually consumed, code quality silently degrades, and delivery dates slip by weeks, then months. The culprit driving this slow decay is developer friction. Developer friction is the debilitating state where engineers spend the majority of their day hunting for system context and asking questions rather than actually writing new code. Traditional modernization tools actively worsen this problem. They rely heavily on static architecture diagrams. These diagrams show the high-level structure of a network, but they completely hide how the system behaves under real-time working conditions. When developers are handed tools that execute blind code translations without explaining the underlying business logic, they are forced into a state of severe cognitive load. Cognitive load is the immense mental strain required to hold complex, fragmented pieces of undocumented system information in your working memory all at once. Overwhelmed by that mental strain, developers inevitably abandon the provided modernization platforms. They fall back on manual code inspection and informal chats to figure things out, causing project velocity to drop and deployment risks to multiply. The math is simple. If a modernization platform fails to meet developers where their daily work actually happens, the entire enterprise initiative will stall out. Codora attacks this problem by reversing the typical migration sequence. Before a single line of legacy code is transformed, the platform prioritizes deep, comprehensive system understanding. Codora's DUM framework, document, understand, and modernize, safely evolves legacy systems. In the document phase, the platform extracts business logic from legacy code. The AI then translates this into file-level documentation and plain English pseudocode, making it accessible to non-programmers. In minutes, this process takes an undocumented black box of lost institutional knowledge and turns it into a highly searchable, persistent database. By solving the documentation gap first, engineers immediately regain the baseline context they need to safely touch fragile legacy code without breaking it. But static documentation is only the first step. To execute the understand phase, developers need to see exactly how the system behaves when it's running. This network graph illustrates a dependency map, a visual web showing how software components rely on each other. Codora runs deep file analysis to build these maps, revealing the exact ripple effects a single code change will have across the entire network. The result is a living system blueprint. It establishes a single, validated source of truth, completely eliminating tool sprawl. Tool sprawl is the chaotic, inefficient accumulation of dozens of disconnected software applications within a single engineering team. Codora takes this blueprint and builds it into an AI knowledge base. Developers can interact directly with their system's architecture using a standard chat interface right inside Slack or Jira. Instead of spending hours tracing an error, a developer can simply type, "Where is the payment logic handled in this module?" and receive a precise, contextual answer backed by the extracted code. Finally, the entire platform moves forward to the modernize phase. The context-aware AI performs safe, semantic transformations tailored specifically to the system's needs. Semantic transformations are intelligent code conversions that preserve the original meaning and business rules of the software, rather than just blindly updating the syntax. Turning a tangled legacy architecture into an interactive, fully understood entity strips away the friction that normally brings migrations to a halt. When system intelligence is built directly into the process, rather than manually pieced together by tired engineers, cognitive load plummets. The daily developer workflow repairs itself. It satisfies the triad of actual developer needs: the context to understand system behavior, the confidence to know the exact impact of a change, and the resulting speed that comes from working without hesitation. This newfound confidence naturally eliminates defensive coding, the practice of writing overly cautious, redundant code to prevent unlikely errors. It also stops the constant interruptions to SMEs, or subject matter experts, the veteran engineers who hold all the legacy system knowledge in their heads. That individual velocity rolls up into major enterprise metrics. Projects experience a massive drop in downtime risk and a stark reduction in technical debt. Technical debt is the hidden cost of future rework, directly caused by taking easy, short-term coding shortcuts today. This bar chart compares the financial impact. Relying on an AI-driven, context-aware conversion reduces total modernization costs by roughly 38% compared to standard market benchmarks. But all of these metrics hinge on one reality. A modernization platform's true value depends entirely on whether developers voluntarily adopt it into their daily routine. Code succeeds because it turns a high-risk code rewrite into a measured, AI-guided evolution. It gives engineering teams the exact intelligence they need to confidently dismantle the past and seamlessly build the future.